Hello and welcome to SciLux, the podcast where we talk about scientific developments and technological changes in Luxembourg. As usual, proudly powered by Research Luxembourg and recording at the Media Center of the University of Luxembourg. And in today's episode, we have two guests. So the first guest is Professor Taniguichi Masanobu from Waseda University in Japan. He is currently visiting the University of Luxembourg on an Institute of Advanced Studies Distinguished Grant. And he's a specialist in time series. And then we have Sophia Loizidou, who is a doctoral researcher at the University of Luxembourg. And her PhD focuses on directional statistics. Sophia and Masanobu, thank you very much for coming today.
Thank you for having us.
Thank you very much.
Okay, so we have two different branches of statistics that I will try to combine. And I want to start with you, Masanobu. The first question, I took your book. So I looked at the title of your most famous book, and I didn't understand anything. So my first question to you is, if you can help me, what is a time series?
You have a lot of time series around you. For example, if you look at the stock price, it's exactly time series. And if you check the temperature every day, then it's a time series. And also, you check your brain wave, it's also time series example. And also, here, the ground is very stable. But in Japan, we often experience the earthquake. Earthquake data is exactly time series data. So if I say more correctly, time series data is a series of random sequence, but evolving with respect to time. This is an important point. Anyway, you can look at a lot of time series around you.
Okay, so also I would say that the data when someone said something in this interview will also be time series, right? Because we have time. There's always a relation to time. No?
Not correct.
No,
so
okay.
It may be depend on space. There are a lot of spatial time series. So if you look at the trading effect for Luxembourg, it's extending the various direction. It's a sort of space time series. Yeah, there are a lot of concept, very general time series. But usually, if I say time series, it depends on time. But it's not time is not essential.
Okay, so there is a name, but it is confusing in a way. But when we have directional statistics, which you specialize in, there is always a direction, or not?
Well, there is always an angular component in it. So when we're talking about directional statistics, it means that we're dealing with statistics on nonlinear manifolds, which in simpler words means that we're no longer on the real line, but we're dealing with data on the circle, on the sphere, on the torus, on the cylinder.
Why do you need to put your data on a sphere or a torus? I mean, data is an Excel table. It's not a sphere.
Yes, so the simplest example you can think of is actually time. So if you want to collect a bunch of time points and represent them just when an event happened, putting it on a linear scale, on a linear plot would be confusing, because then you're not sure where it starts and where it ends. And it's not exactly clear that the start point and the end point are actually the same point. So a better thing would be to plot them on a circle where it is clear that the beginning and end, usually we denote this by 0 degrees and 360 degrees or 0 and 2 pi. These points are the same. So if you plot them on a circle, then you can clearly see that this is the case. And then we can go to more complicated shapes. So for example, a sphere is a more complicated shape where we have a similar problem. A torus that I mentioned before, the shape when we have a two-dimensional torus is basically the donut shape. If we go to higher dimensions, then we can no longer visualize this shape. The torus, the mathematical definition for it is that the Cartesian product of circles. So if we have a lot of circular data, then we have a torus. And then we also have a cylinder where, well, we know that the base of a cylinder is a circle. So there we also have angular data.
I think I'm following you, but still I need real life applications. So you mentioned time, but what exactly, what kind of data, what we called it circular data in this case, right? For circular plots, can we use in this case?
Yes, I already mentioned time. Another example would be the direction where the birds fly. This is, again, angular data that you can represent on the circle. Going to more complicated examples, if we're talking about the sphere, then we might consider space data. So we know that the Earth is a spherical object, so things that are happening around the Earth can be considered in this domain. For the toroidal data, we have one very interesting example is protein folding. In our body, we have proteins that have to fold in a specific way. And if they don't fold in the way they're supposed to, then our body does not do the things it's supposed to do. It's important for scientists to be able to know how this folding is supposed to happen and to be able to check if our proteins fold in the correct way. And when I say folding, I mean that the proteins take on a specific shape. And so between the bonds, there are specific angles happening. And so these angles can be represented on a torus because we have a lot of angles. And when we're talking about cylindrical data, then we can consider earthquakes, or another example is considering wave direction with wave height or wind direction, again with wave height. So it's basically data that we can collect from the sea.
Okay, a lot of examples. You mentioned earthquakes, so I'm going back to Masanobu for earthquakes, as you are one of the few Japanese people I get to talk here. We don't have a lot of visiting professors from Japan. I don't know why, right? So you'll be a specialist in statistics and in Japan too, so two different things. But first, for coming back to what you were saying about the time series, that's only one concept that people, especially the ones who deal with statistics, are familiar with. But then I have to look at my notes. We have asymptotic theory. Yeah. What is that?
Yes. Suppose you observe the time series, one time series, and the length is, say, n length. So usually, if you observe such time series data, many people construct a statistic. Also, some want to estimate the distribution. But for example, the n is just 10. It's possible, but you observe the 1,000th length time series and then construct a statistic, then derive its distribution. It's a very hard task. So time series people often use the approximation of distribution. Then we say the distribution is asymptotic distribution. So that implies if the time series length tend to infinity, then what's the shape of distribution? Philosophy is something like this. So then if you focus such approximated distribution, we use asymptotic theory. So if you are time series analyst, many of them use asymptotic theory because the exact distribution is very, very complicated. It's essentially difficult to derive such a distribution, except for very, very elementary statistics. So we often use asymptotic theory. Please understand, asymptotic theory is just time series length tend to infinity, then statistic and its distribution. How is its distribution? How the statistic is good or not? So if you length of observation tend to infinity, what will happen? This is asymptotic theory. Very simple.
Very simple. I don't think so. For you, maybe very simple. This is already becoming, so difficult for me to imagine, right? But we're still kind of watering it down a little bit because you mentioned the word distribution. Yeah. And I wanted to ask Sophia about it because that's one of the things I see everywhere. If I read statistical papers, we're always talking about distribution. So what is it and why is it important for statistics?
So distribution is a mathematical function that gives the probability of different outcomes happening. And it's also a way to model data and quantify the uncertainty around events happening. The simplest example I can think of for distribution is when we throw a coin. So if the coin is fair, we know that we have a 50% probability of getting heads and 50% probability of getting tails. Now, in this example, we have a discrete outcomes. which means that we have only specific values that our outcome can take. Another example of this would be throwing a die. Then we have the outcomes 1, 2, up to 6. And we know that for each one, we have a probability of 1/6 of getting it. Going to more difficult examples would be to consider continuous outcomes of experiments. So one example of that would be, imagine if we're trying to model the height of people. So then we could have any number between, let's say, 30 cm for babies, and then we go all the way up to 2 meters and 10 cm for very tall people. So we can have any number of these. So this is what is called a continuous outcome.
Okay, and you mentioned probability theory as such. This is when my knowledge of statistics finished, right? So I had to do probability calculus at school, and I have to say I never liked it. I have a feeling that in this podcast I always say what I didn't like, but anyway, because it was for me difficult to understand that on average this will happen. So it was never for me 1 + 1 is 2. It was very much kind of a difficult interpretation. But still, this is basically where the school knowledge of statistics finishes, I would assume. So what do you think, if you look at your research right now, how long is the path from the probability at school and what you're doing right now?
Well, if you mean directional statistics, then it's quite far. I mean, we do still use averages, but even that simple quantity has to be redefined for the directional world. And I will give you an example for why that happens. So imagine you want to take the average of 1 and 359. Then if you do it with the classical way, then that gives you 180. But if you're on the circle, then degrees 1 and 359 are, say, at the top. And then degree 180 is right at the other end of the circle. This is just one simple example of things that have to be redefined. And so, yes, what I'm doing now, it's very far from what I was doing in high school. But if you're talking about more general probability theory and statistics, personally, I did A-levels in mathematics. So I already knew quite some basic stuff about this kind of things. For schools in Cyprus, this level was a bit lower for the things that we learned there in the public schools. To be honest, I'm not sure what is happening in Luxembourg.
Yes, I can't say that either. Once my children get to that age, I will tell you what they are doing exactly. But I know that you prepared a pub quiz question related a little bit to more kind of common knowledge of probability. But before you ask that question, I wanted to ask Masanobu. Yes. How is mathematics at school? What do you think? All the Japanese children are good at mathematics or not?
Oh, not all, but some of students are very good at mathematics, and some of them have very high ability. Yeah. So that's true. But if you look at general Japanese student, so elementary level, this is not true. Nowadays, so you have a cell phone or a PC, so they need not to do actual calculations. So maybe that went down, their ability. All the day, I learn by my heart. From 1 by 1 to 9 by 9. So I met Indian researcher in India. Some people can learn by heart from 1 by 1 and 1990 by 1990. So there are such aspects of fundamental mathematics. In the old day, Japanese elementary students are good at such matter. But I don't know now.
And you also teach at the university, right? So what about your students? Do you see a difference of their knowledge before and now?
Nowadays, there are big variation. Some of them are very, very excellent, but the others are not even graduate students of Waseda University. Some of them are very low level.
Yeah, I guess this is a struggle that was always there. But we have one brilliant PhD student here, as you can see. She knows a lot. And we go back to you, Sophia, for the question. So let's now look at the pub quiz question that you prepared for our listeners. And listeners, remember the answer only at the end of the podcast. So you need to listen to the whole thing.
So if you meet a person on the street, then the probability that you and them have the same birthday is around 1/365. And this is ignoring leap years to make it simpler. So how many people do you need in order to have probability of at least 50% that two of them share a birthday?
So now I hope everybody is taking out a pencil and the paper and calculating that, right? We just discussed it. Or maybe in their minds. Maybe we have some Indian listeners who are just calculating it in their minds. Everything is possible. Thank you very much, Sophia, for that. And remember the answer only at the end of the podcast. And now we're coming back to that theory and when my brain was getting a little bit confused already. So Masanobu, we said already asymptotic theory, but that's not all. We have something called higher order asymptotics. What's this order here doing?
This is a very, very special topic. So I visited a lot of foreign universities. Most of them dislike these topics. So first I mentioned the asymptotic theory. Asymptotic theory is the approximation of distribution. So this is a main approximation, okay? But if main approximation does not work, we calculate the second main order. We say this is the second order asymptotic theory. So more accurate, we calculate more accurate approximation. And then that implies the second order approximation. But if the main order and the second order approximation does not work, we calculate the third order approximation. Then we say that this is the third order asymptotic theory. So if you mention second order and if you mention third order approximation, then we are discussing a high order asymptotic theory. So this is a very special field. So the approximation, main order, second order, and the third order. Then the approximation might be good, but calculation is very hard. And the approximated formula become very complicated. Actually, so some people not so appreciate, but I appreciate. When I was young, I wrote a lot of such papers. So, for example, if I wanted to write one paper, I need 100 report paper. And also, this calculation is very severe because 100 pages report paper, even if one mistake, so the conclusion will be very different. And the conclusion is disorder. So I can immediately understand my calculation was wrong in some stage. So it's a very hard work. So, but nowadays, PhD students dislike high order asymptotic theory. So it requires such labor for calculation, 100 pages calculation, and you should check each formula. So maybe nowadays young students dislike this matter. So maybe Sophia dislike. Joke.
I think I should not ask you whether you dislike it or not, because this is risky, right? But yeah, it sounds very complicated. And is it something you would look at? Because I know one of the applications you are interested in is the portfolio composition, right? Yeah. So we're moving to the financial data. Are you applying these methods to portfolio composition, or it's something completely different?
No.
Okay, I'm confusing.
We could apply such a high order method to estimate the portfolio coefficient. It's possible. Yes.
Okay, all right. But in general, what are the methods that are used? In my past life, I was actually working with communication of fund industry. So I kind of understand how the portfolio is composed. It's very discretionary. So the investment manager says, okay, I think this would be, of course, basing on the data. But what are you suggesting? What is your approach to portfolio composition?
I use a very modern statistical tool. So this is a very special naming, local asymptotic normality. So first we establish such a concept for the asset time series data. Then, based on the local asymptotic normality, we can specify the optimal estimator. So my proposal is to use optimal estimator for portfolio coefficient.
And this is also something you're working on right now in the project?
Yeah.
Yes. So
not this project, but I still
too many
continue.
projects.
Yeah, I still continuing to this one. So, may I tell the answer?
Yes.
My conclusion is to use a maximum likelihood estimator for portfolio coefficient. This is my answer.
Okay.
But if I talk with actual financial people, they still use classical portfolio estimator, which is called mean and variance portfolio. This is very classical and very simple one. So I suggested to use a maximum likelihood estimator, but such actual people were not interested in to use such a theoretical estimator.
And this is a challenge for statisticians in general, right? Because a lot of the work you're doing would be so useful for so many other specialists, like, for example, social scientists. And I have a lot of friends who studied social sciences and they kind of complained, I had to do statistics and it's so difficult. So, Sophia, how is it going? Is it difficult to convince social scientists to use your methods? Are they using directional statistics? Can you say, okay, now you just apply your data on a torus and it's clear, or not really?
Well, first of all, in social sciences, there do exist a lot of data that are circular. So one example is in criminology. Maybe the time of day when a crime happens is important, or maybe the day of the year when the crime happens is important. And in both cases, we have this circularity where, for example, the first day of the year follows the last day of the previous year. The problem is that most often statistical papers are too theoretical for people from other disciplines to be able to use what is being written there. And it's actually important for us statisticians to work with people in other domains. For example, for me, I have worked with people in other domains. The example I mentioned in the beginning with protein folding, I spent some time in Copenhagen working with bioinformaticians and computer scientists, trying to understand how their data works, how this protein folding works. And I was trying to explain to them how our distribution works, what they have to be careful with, how they should code it.
And now they know everything.
I would hope so.
Let's hope, right? Because this is so important, this dialogue between different disciplines. And that's what's happening with the project you are also in. So the time data project, right? So you're here and I'm very happy because this project involves two of my former guests. So I already interviewed Professor Christophe Ley, of course, but I also interviewed Professor Diane Pierret. So two people I already knew. And I just wanted to ask you, what are you working on as part of this project? Because you said a little bit, but not exactly. So what is it? I guess a lot of dialogue. And what is your expertise in it?
So it was 2020. I wrote a very fundamental paper. Coincidentally, I could find the directional distribution and time series spectral distribution has similarity. I could recognize that point. Then I could introduce a very general directional distribution from time series spectral distribution. These two are very different.
Exactly, right? Yeah. Because we were separating them right
so
now.
Time series people do not know directional distribution. Directional people do not know time series spectral analysis. But coincidentally, I could recognize this important similarity. I could write one paper So this provided the new issue. So the advantage of our approach is I use the time series spectral distribution to define the new, very general, new directional distribution. But historically, in time series area, there are a lot of natural parametric model, nested parametric model. Then, if you get the data, statistician want to select the which model is appropriate. We call this is model selection problem. For time series people, it's very natural. There are a lot of candidates for statistical model. Then this is easily will be done. But if I look at the directional field, so people use a very famous fundamental distribution. The model candidates are not so many. So then our approach introduced a new aspect in directional field. So that's the beginning of collaboration, Luxembourg people and me.
Okay, so hopefully one day, Sophia, with directional statistics, will also be doing some time series in directional statistics.
Yeah, I'm inviting, so to co-work.
Yes, exactly. Why not? Why not? You can't see right now in the studio, they are sitting on opposite sides. So, I'm imagining this bridge that would come, right? So, and it's interesting also to say, because we have a tendency, us lay people, to say statisticians, and we put you all together, right? But you just said time series people and directional people, right? And probably there are many different groups that are in the small bubble that don't cross. And you said, we need to cross, and you crossed, right? And this is always very, very interesting. As we are in a science podcast, I'm always interested in applications and how you can use data and hear statistics and different contexts. And we met before, Masanobu, and you got me very interested because you said, I'm thinking about statistics and opera. So I have to ask you about this because for me, this just doesn't come together. So what is it?
Okay. So now we just started. We haven't no result, but maybe we have a connection with the baritone singer, soprano singer, and opera singer. We have a lot of information. I'm an amateur person for opera, but I just know the composer Verdi, he was called the king of opera. So people in opera respect him very much. Then there is some tool to transform the musical note to data. And also, if you observe the acoustics data, then we can translate it to the numerical data. Then we get a time series, a sort of time series. So there is a very important topic, principal component analysis for time series data. So the principal component just implies what is the most important factor for the Verdi's composition data. So first, we wanted to detect such the important principal component. This is our first purpose. But the next purpose is causality. Causality was introduced by econometrician Granger, who got the Nobel Prize in economics. So first, he defined the causality concept for two time series, economic time series. Which one affects the other one? Simply, I can say. Such a method are now extending the variety of fields, gene data or very abstract data, graph, and such topological concept. So now we want to apply causality method to Verdi's composition. For example, if you get the other composer's composition, then we are interested in, is there any causality from this composer to Verdi? So this is a very interesting point. But this is near future work. Now we are just thinking of this.
But it's very interesting, and I can see you got very excited, right? You even touched the microphone because you got so excited. So I can see there is a lot of passion for the music, right? And it's interesting. What about you, Sophia? For the future, I know you're focusing on the PhD right now, but let's say we can just imagine the next paths you would like to follow. Is there any place where you would like to apply directional statistics or some field? I know that there is a lot of studies here at the University of Luxembourg done in sports analytics as well. Is it something that you would also like to overlap? Let's talk dreams right now.
Well, one of my favorite things to watch is football. So it would be great if I could find a way to apply what I'm doing in football data to help their data science teams, but it's a long shot.
Is actually the direction of a football player gathered as data? Do you know that?
I'm not sure if they have GPS trackers on them, but for sure, at least for the big matches, there are cameras that capture everything, and using AI, they can know where every player is at each point.
So I'll be watching for opera and for football, and I will ask you hopefully about the results at a certain moment, or maybe something else. Who knows? This is just a dream sphere here, a beginning of a new project. And well, I think looking at the clock, this is the moment to go back to the pub quiz question that Sophia asked. So as usual, can you please remind our listeners what the question was about and then give us the answer?
The question was, how many people do we need to have probability of at least 50% of two people sharing the same birthday? And the answer is 23.
Only?
Yes.
That's really not much. Okay, I'm very surprised. I'm going to check that because I can't believe. I'm sure you're right. I'm joking. Okay. Do you know anyone yourself who was born on the same day as you?
Yes, I know at least 4 people that share the same birthday as me.
Okay, so you know more than 23 people by 4.
Yes.
That's good. Masanobu, do you know anyone who was born on the same day as you? Who has the same birthday?
No. I've never met such a person.
No, you see. So, but of course, we are talking statistics, right? So this is absolutely not a sample that would confirm. I think I don't know anyone either who was born on the same day as me. So fair enough. Good to know. So thank you so much for coming, Masanobu and Sophia. And yes, hope you enjoyed the show.
Thank you.
Thank you very much.
And this is it for today. Don't forget to subscribe, to follow us, to check what we're writing on all the social media, suggest guests or questions. And as usual, the next episode comes in 2 weeks' time. My name is Hanna Siemaszko, and this was Silax.